Inside your computer are dozens of microchips with tens of billions of transistors. You may know that these transistors are the cornerstone of all technology, are manufactured in multi-billion-dollar factories, and are only a few nanometers in size. But what you may not know is that this network of billions of transistors is actually organized a lot like Lego bricks connected together in order to build a Lego set such as this 7,541-piece Millennium Falcon. Transistors are like Lego pieces. In this video, we'll explore how the transistors inside your computer are like Lego bricks, what transistors actually look like, how they perform basic logic, and finally, how 26 billion transistors are organized into the different sections of the CPU. So let's dive right in. Let's begin with exploring Lego bricks and Lego bricks versus transistors in standard cells. In this analogy, we'll equate one transistor to a single stud on a Lego brick. On their own, neither one does much at all. However, when a few transistors are connected together, they form a standard cell, which is the fundamental building block of every CPU and GPU. Similarly, multiple studs form a Lego piece, which is the building block for all Lego creations. For example, 2 transistors connected together form an inverter standard cell, 4 transistors connected together form a NAND gate, and 6 transistors form an OR gate. There are many other standard cells built by connecting transistors together, and similarly, there are a wide range of Lego pieces with varying numbers of studs and shapes. But before we explore some of the more complicated standard cells, we first need to understand how one of the simplest standard cells works. Let's examine the inverter, which is analogous to a 1x2 Lego brick. Its function is simply to take an input of a 1 and output a 0, or vice versa. This inverter has a logic symbol like this, and the standard cell look like this. Essentially, standard cells like this inverter are the real-world physical structure of a logic gate, and it's what you would see if you could open up and zoom into a nanoscopic view of the processor in your smartphone. So, let's see how it works. At the bottom of the standard cell are 2 transistors built on top of a silicon base. We'll focus on one of these transistors, which has been simplified a little bit for the sake of this explanation. Inside this transistor are a few key parts: the gate, the channel, and the dielectric, which is a barrier that separates the two and prevents electricity from passing through. Additionally, on either side of the channel and above the gate are metal contacts connected to vertical vias that are used to input and output electricity to the corresponding parts. So, how does this transistor work? Well, when 1 volt is applied or input to the gate, electricity can flow through the channel, essentially connecting one side of the channel to the other side of the channel. However, when 0 volts is applied to the gate, electricity cannot flow through, resulting in electrically separating or isolating the 2 sides of the channel. A quick analogy is to think of the channel and gate as a water faucet and handle. When the handle is turned on, water can flow, and when the handle is turned off, the water is stopped. The name of this transistor is an N-type FinFET due to its fin-like shape. Here's the symbol for a simple N-type transistor, and again, when 1 volt is applied to the gate, electricity can flow through the channel. Let's bring in a second transistor over here, which is the same FinFET shape but functions a little bit differently and is called a P-type transistor. Specifically, it's designed to operate in the exact opposite fashion, where when 1 volt is applied to the gate, electricity cannot flow through the channel, and when 0 volts is applied to the gate, electricity can flow through. Using our water faucet analogy from before, this transistor is like a faulty water faucet where when the handle is down, the water is on, and in order to turn the water off, you have to actively lift the handle. This is the symbol for the P-type transistor, and the circle on the gate indicates the inverted functionality. Now that we have 2 transistors, one N-type and the other P-type, let's connect the gate between the 2 and merge the input gate contacts together into a single contact. As a result, a single input voltage on the gate, which can be either 1 volt or 0 volts, travels to the shared gate that controls both of the transistors, and as a result, the N-type transistor turns on and the P-type transistor turns off. With the N-type transistor on, electricity can flow through its channel, which results in 0 volts from the ground rail traveling through the local interconnects, down a vertical via, through the channel of the N-type FinFET, then back up a vertical via on the other side across a separate section of local interconnects, and finally to the output, thus turning a 0 into a 1. At the same time, the N-type transistor is off and this section of wire is isolated. One thing to note is that while these wires may look like they're floating three-dimensional structures, all of the empty spaces are in fact filled with insulating material called dielectric. This may have been a rather long explanation, but truly understanding the basic function of the inverter standard cell is critical to understanding the more complicated ones, such as this NAND gate, this AND gate, or this exclusive OR gate, which we'll discuss in a little bit.